For this lab, I chose to examine conservation of momentum during collisions. The system I chose was a tennis ball colliding with the ground and bouncing back up several times. I chose this system because it's simple to model but has interesting characteristics to examine, such as if the collision with the ground was elastic or inelastic. In this lab, I will determine if the momentum was conserved within the system, determine if the collision was elastic or inelastic, and examine the conservation of total energy. The significance is using a simple ideal system to understand basic principles that can be applied to more complex systems. Here I have some initial properties of the system, such as the mass, diameter, initial and final velocity, the net force, and the assumptions I made on this system. I assumed this was an isolated system, so no total energy was lost from the system. In an isolated system, momentum is conserved during a collision. If we have two objects colliding, we know that there must be two forces present, which is the force of object 1 on object 2 and the force of object 2 on object 1. We know from Newton's third law that these are equal and opposite forces. The duration of the collision is also equal for both objects. Therefore, the impulses are equal and opposite. Impulse is equivalent to m times delta v, or the change in momentum. By rearranging, we can obtain the following equation, which states that the total final momentum of the system is equal to the total initial momentum of the system. Here's a more general form for more than two objects. Elastic versus inelastic collisions. In elastic collisions, no kinetic energy is lost to the surroundings, so it is all conserved in the system. There's no change in internal energy, meaning there's no change in shape, temperature, or any kind of vibrational energy. This is most applicable to idealistic systems. Inelastic collisions, however, do involve some kind of change in vibrational and kinetic energy and are more applicable to realistic systems. Here's my experiment in Tracker. Using the data from Tracker, I made a plot of the y position of the ball over time. As you can see, with every bounce back up, the ball does not reach its max height from before. It cannot do this because the force of gravity is continually acting on the ball. Here's a closer look at the ball's first collision with the ground, which I will be examining in more depth in the coming slides. I used Newton's second law to calculate the momentum of the ball the instant right before the collision and the instant after. So to calculate the momentum before the collision, the initial momentum is right as the ball is dropped, where the velocity is 0. The net force acting on it is only due to gravity, since I chose to ignore air resistance. The time taken for the ball to reach the ground was 0.5 seconds. Therefore, the momentum of the ball the instant before it collides with the ground was 0.285 kilogram meters per second. To calculate the momentum of the ball immediately after the collision, I used a similar process. Here I considered the final momentum of the ball to be when it reaches its max height. The velocity at this point is equal to 0. Again, assuming negligent drag, the net force is due to gravity. So I got the momentum after it collides with the ground to be equal to negative 0.186 kilogram meters per second. Using the initial and final velocities I calculated on the previous slide, I calculated the initial kinetic energy of the ball and the final kinetic energy of the ball after collision. As you can see, kinetic energy within this collision was not conserved. However, this does seem like a large loss for such a small collision. In any case, the tennis ball colliding with the ground is not an elastic collision, because there is some deformation of the tennis ball as it hits the ground. Thus, there is a change in vibrational energy. Here is a video showing how the shape of the tennis ball changes as it collides with the ground. I had several possible sources of error in my experiment. The systematic error can be attributed to a low video frame rate, which caused tracking of the object to be difficult. Also, the camera orientation may have affected the position data. In addition, it might have been better to track the initial and final velocity rather than calculate it from position data. I also made several assumptions in this lab. I assumed that this was an isolated system, so there was no air resistance, no friction, and therefore no loss in thermal energy. I also assumed that the motion was only in the y direction, when in reality, the object was moving in the x, y, and z directions. These sources of error could be addressed by using a better camera, better tracking equipment, and a more isolated lab setting. That's the end of my lab, so thank you for a great semester.